In this lesson, we are going to take a look at solving systems of linear equations by graphing once again, but today we're going to talk about some special cases that occur when we are solving these systems by graphing. So let's go ahead and jump in here to number one. And when we are solving these, we want to pay close attention to the slope and the intercept of these equations, as that's going to help us kind of figure out a pattern for when these special occasions are going to occur. So in number one, we have the linear equation y equals negative 2/3 x minus 1 and y equals 1/3 x minus 4. So if we were to graph this first equation here, our slope is negative 2/3 and our y-intercept is negative 1. And we always start by graphing our y-intercept, so that's negative 1 on the y-axis. And from there, our slope tells us to go down 2 and right 3. So from this point, we're going to count down 2 and right 1, 2, 3, and make our new point. And then we can continue that pattern going down 2, right 1, 2, 3. And we get the line of the linear equation, y is equal to negative 2/3 x minus 1. Okay, let's go ahead and do the same thing for our second linear equation. We have the equation y equals 1/3 x minus 4. So the slope of that line is 1/3. The y-intercept is negative 4. So if we were to graph that, we start with negative 4, our y-intercept on the y-axis there. And our slope of positive 1/3 tells us to go up 1 and right 3. So from our y-intercept, we're going to count up 1 and right 1, 2, 3. Up 1, right 1, 2, 3. And there we have the line of the graph, y is equal to 1/3 x minus 4. Now, as we talked about previously, the solution to a system of linear equations, when we graph it, is the point where they intersect. So these 2 points intersect right here at the point 3, negative 3. So the solution to this set of linear equations, the system of linear equations, is the point 3, negative 3. Okay, let's go ahead and take a look at number 2 here. This is special case number 1, and let's talk about it here. So we have the system y equals x plus 3 and y equals x minus 4. So let's go ahead and graph this first line, x plus 3. So the slope of that is 1, which is the same as 1 over 1, and the y-intercept is equal to 3. So if we were to graph that, our y-intercept is 3. We start with 3 on the y-axis, and our slope is positive 1, so that's up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, because 1 can be written as a fraction 1 over 1. Okay, so there we have the graph of the line y is equal to x plus 3. Now let's go ahead and graph that second linear equation, y is equal to x minus 4. So the slope of this equation is 1, because there's a 1 in front of that x, even though it's not written, which is the same as 1 over 1. And the y-intercept here is negative 4. So right off the bat, you might be noticing, well, that these lines have the same slope, and they do. So let's see how that affects our system here. If we were to go and graph this second line, we start with our negative 4 y-intercept, that's right here, and our slope of 1 over 1 tells us to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So we can continue with that pattern, up 1 over 1, to get the line of the equation, the graph of the equation, y is equal to x minus 4. Now when we graph systems of equations, we said the solution point is where our lines intersect. Well, these lines are parallel. They're never going to intersect. And when that's the case, what that means is since our lines are not going to intersect, there are going to be no solutions. Okay, and that's going to occur here when our intercepts are the same, or sorry, when our slopes are the same. If our slopes are the same and our intercepts are different, okay, it means those lines are going to be parallel and there's going to be no solution. Okay, sliding over here to number 3. Number 3, I'm going to slide over a little bit. We have the equation y is equal to negative 3x minus 1, and 3y plus 9x is equal to negative 3. So first thing I'm going to do here before I start graphing anything is let's go ahead and convert this second equation into slope-intercept form. So we need to solve for y. So to do that, we're going to subtract 9x from both sides. When we subtract 9x from both sides, we get 3y is equal to negative 9x minus 3. And if we divide all of these by 3, we will have the equation there in slope-intercept form, and it'll be y is equal to negative 9 divided by 3 is negative 3x, and negative 3 divided by 3 is negative 1. So we're looking at y is equal to negative 3x minus 1. All right, let's go ahead now and graph these, and you might notice here that we are actually dealing with the same exact line here. Let's talk about what happens when that's the case. So if we were to graph this one, the slope is negative 3, and the y-intercept is negative 1. So we would start by graphing negative 1 on our y-axis, and a slope of negative 3 tells us to go down 3 and right 1, down 3 and right 1. Or we could go up 3 and left 1 and get that same pattern. Okay, so there's the line, there's the equation, the graph of our first line there. Okay, well, if we went and graphed this second equation, it's the same exact line, so it's going to be just the same exact thing right over the top of our first line. And I'm doing my best here. Make sure you draw these with a straight edge. So let's talk about what that means for our solution. Okay, the solution to a system of linear equations, as we talked about in number 1, is where our graphs intersect, where they are touching. Well, on this graph, since our lines are right on top of each other, okay, every single point on that line is going to be a solution to this system of linear equations. Okay? And since that line goes on forever and ever and ever, it means there are an infinite number of solutions. So whenever this is the case, when the system of equations is the same exact line, okay, when both of the equations are the same exact line, that is a case where there are infinitely many solutions, or what we abbreviate as IMS, stands for infinitely many solutions, because every single point on both of those lines is a solution set, or is part of the solution set. So there we have it. There are 3 options really when we are talking about solving linear equations. Okay, we can either get a single point like we did in number 1. We can get no solutions like we did in number 2 because the lines are parallel. Or if the equations turn out to be the exact same thing, there is an infinite number of solutions, or infinitely many solutions. Okay. Let's go ahead and scroll down to 4 through 9 and talk about how we can determine if these systems have one solution, no solutions, or infinitely many solutions by just looking at the systems. So I'm going to scroll down here. Okay. And before I do that, let's quickly talk about this. So the biggest indicator here is going to be our slope. Okay. If you notice in number 1, the slopes were different here. All right, we had a slope of negative 2/3, and we had a slope of 1/3. Anytime the slopes are different, we are going to get one solution. Okay. For number 2, okay, we made a note of it. Our slopes were actually the same, and our y-intercepts were different. So if the slopes are the same and the y-intercepts are different there, that's when those lines are going to be parallel, and we're not going to have any solutions. And then lastly, the third one should be the most obvious. Whenever we are dealing with 2 equations that are the exact same thing, so y is equal to negative 1/3 x and y is equal to negative 1/3 x over here, okay, that's when there's going to be infinitely many solutions. So really what we need to identify here is we need to identify our slope, and that's going to tell us a lot about these systems. So let's scroll down here and talk through these problems 4 through 9. So it says, without graphing, determine if the following systems have one solution, no solutions, or infinitely many solutions. Okay, so for number 4, we have the system y equals 1/2 x plus 4 and y equals 1/2 x plus 7. So right off the bat, you should notice that the slopes of these 2 lines are the same and the y-intercepts are different. So whenever the slopes are the same and the y-intercepts are different, that is when those lines are parallel and there are going to be no solutions. Okay, right when you see those same slopes, you should be thinking parallel lines. Okay, for number 5, we have the system of equations y is equal to 7x plus 4 and y is equal to negative x plus 7. So the slope of that first line is 7. The slope of that second line is negative 1. Anytime the slopes are different, okay, that's going to be one solution. And that's all we're trying to determine here, if it has no solutions, one solution, or infinitely many solutions. All right, sliding over to number 6, give us a little space to work here. Whenever we see an equation like this second equation, we're going to want to convert that to slope-intercept form right away. So to do that, we're going to to do that, to get y all alone, all we have to do is divide by 3. Okay, and all these equations. When we divide by 3, we get y is equal to 3x plus 5. And now we can go ahead and take a look at our slopes and determine whether there's one solution, no solutions, or IMS. So the slope of that first line is a positive 3. The slope of the second line is a positive 3. And since they have different intercepts here, that means those lines are going to be parallel. Okay, they have the same slopes, but they're not the exact same lines. Those lines are going to be parallel. And when the lines are parallel, that means there are no solutions. All right, a few more examples of this. For number 7, we're actually going to have to solve both of those equations for y. So let's start with that first equation. 2y is equal to 4x plus 12. And then we have the equation 2y is equal to 4x plus 10. Okay, to solve the first equation, to get y all alone, we're going to get rid of that times 2 by dividing by 2. And when we divide by 2, we have to divide every single term in that equation by 2. So when we do that, we're looking at y is equal to 4 divided by 2 is 2, so that's 2x, and 12 divided by 2 is positive 6. So our equation there is y is equal to 2x plus 6. If we do the same step here on number 7 to get y all alone, we're going to have the equation y is equal to 2x plus 5. So let's take a look at what we're dealing with here. We have a slope of 2 and a slope of 2. Okay. And since they're not the same exact line, right, they have different intercepts. Those slopes are the same, the intercepts are different. Those are parallel lines, which means there is no solution to this system. Okay, and the more you practice this, the more you work on graphing these, the easier it will be to see when you're just working with these systems. Okay, sliding over here to number 8, just going to put a little line there to divide it. For number 8, we have the system y is equal to 2x minus 6 and y is equal to negative 2x plus 4. So we have a slope of positive 2 and a slope of negative 2. Since those slopes are different, as soon as you see those slopes are different, we know there's going to be one solution. Okay, there's going to be one point where those lines cross. Okay. And then finally, taking a look at number 9, we have the equation y is equal to 2x minus 6 and y is equal to 2x plus 4. So those equations there, we have a slope of 2 and a slope of 2. So those lines are going to be parallel because they have different y-intercepts here. All right. So when we have parallel lines, there are going to be no solution. Okay. When would we have a case where there is infinitely many solutions? Well, let's say I'm going to slide over here and give you an example of that quickly. Okay, anytime you end up with the same exact equation. So say we had y is equal to 2x minus 6 and y is equal to 2x minus 6. Okay, that is a case where there are infinitely many solutions. When these two equations are exactly the same. Right, 2x minus 6 and 2x minus 6. Okay, so there are 3 options when we are solving solving systems of linear equations. We can have one solution, no solutions, or infinitely many solutions.